Welcome to the course on network information theory. Today I am going to talk about source coding problem. So, we are going to look at how we can do source coding of a discrete memoryless source, and we are going to start with block to variable length coding. So, in this lecture I am going to talk about what is a prefix free code and what is a condition for existence of the prefix free code. That is this craft inequality, and then I will give example of one such prefix free code, which is Shannon-Fano code, and subsequently in lecture 5 I am going to talk about optimal block to variable length coding, which is Huffman coding. So, I will start with how do we encode a single random variable. So, I am considering a single random variable, and I am going to talk about which can take basically let us say k values, and each have some probability p1, p2, p3, pk. So, how do we encode such a random variable using block to variable length coding? And then I will define what is a prefix free code and condition for prefix free code, and then I will define something called rooted tree with probability, and I am going to use this to derive expression for what is the expected code word length. What is the minimum, what is the lower bound on the, what is the minimum expected code word length required to do this source coding. Okay, and then I am going to give an example of a particular prefix free code, which is Shannon-Fano coding. So, this is a problem I am looking at. I have a message source that is emitting a k-ary random variable. When I say it is a k-ary random variable, you can take k different values. So, let us call it u1, u2, u3, uk, and they are happening with some probability. Let us call them p1, p2, p3, pk. So, now this is a random variable that I want to encode. So, what is my objective? I want to represent this random variable in minimum possible bits, correct, because I want to do source compression. So, I am encoding this random variable u into another random variable z, which consists of xi alphabets. So, this x1, x2, x3 is basically, so z is a code word corresponding to u, which consists of a w length code word, where this w is variable and this xi takes values from d-ary alphabet. What do I mean by that? So, this x1, x2, x3, xw, each one of them can take d possible values. Okay. That d can be k also, or in general it is different from k, right. So, what I am doing is I am encoding this single random variable into a variable length code, because my w is variable length. And if you look at it intuitively, what would you like to do? So, u takes k possible values, among them the ones which are happening more frequently, you would like to encode them using smaller number of bits, and the ones which are rarely happening, you can afford to use a larger code word length, right. So, that is basically the idea behind this. So, this w is a random variable. So, clearly our code word is of variable length, and this list of, so this list z1, z2, z3, zk, because there are you can take k possible values. So, for corresponding to each of them there is a code word, I am calling it z1, z2, z3, zk, where each of these zi's are variable length code which are taking alphabets from d-ary alphabet. Okay. So, this list z1, z2, zk is basically a code word for my random variable u. The input u is a k-ary random variable, whereas the output takes alphabets from d-ary alphabet. Now, as I said, zi is a code word for ui, and my code word length wi is variable. So, how do I define the average code word length? The average code word length is defined as, so I have k possible values for UIs. Each one of them takes length. So, ith UI has code word length WI, and probability of its occurrence is PUI, right. So, this I sum it up for all UIs, all k UIs, that would give me average code word length. So, average code word length is length of each of these UI multiplied by the probability of occurrence of that particular UI, and then I sum it over all possible k elements of U. Okay. So, this is my expected code word length. Now, how do I define goodness of a code? Like how would you say a code is good or a bad? A code, so because this is a variable length, basically my WI is variable length. So, if I can reduce my expected code word length, that is nice. So, a goodness of a code is defined by smallness of the average code word length. The smaller is the expected value of W, better is my basically code, right. So, that is what I am saying here. Smallness of average code word length is the goodness of, is a measure of goodness of my code. Now, let us define what do we mean by a prefix free code. So, to define that, I am just going to define in terms of a rooted tree, okay, and I will show that I can map any prefix free code into a rooted tree. So, let me first define what is a rooted tree. So, a Deary tree is a finite rooted tree such that D branches stems outward from each node. So, what is a Deary tree? So, it has a root. So, I am just drawing it like this, it has a root, okay, and there are D leaves basically going out. So, let us say if D is, let us say 3. So, then they will have 3 leaves going from here. I can have 3 leaves going from here. I can have 3 leaves going from here, right. That is a Deary tree. Okay. Now, what is a full Deary tree? A full Deary tree of length n is a Deary tree with d to the power n leaves, each at depth n. So, a full Deary tree is a tree which is full blown. So, it is like if you take this example, so this is depth 0. If I draw here, I will have 3 leaves here, I have 3 leaves here, I have 3 leaves here. That is full Deary tree. If I again extend it, make 3 leaves here, make 3 leaves here, make 3 leaves here, 3 leaves here, that is full. So, basically, so you looking at any depth, all, so that is what I am saying. If you look at, so at depth 1 there are 3 leaves, at depth 2 there will be 9 leaves, at depth 3 basically. So, you will have at depth n d raised to power n leaves. So, that means all the leaves are there. This is opposed to, let us say, look at this case. In this case, what I did was, I did not, there are no leaves going from here. So, this is not a full Deary tree. Okay. So, what I am saying is, a prefix free code can be identified with a set of leaves in a Deary tree. So, what is a, so in a prefix free code, no code word is a prefix of any other code word, right. So, what I am saying is, if you have a Deary prefix free code, we can identify them by a set of leaves in a deary tree. Why this is so? So, from the root to the leaves, there is a unique path, correct? Now, in a prefix-free code, no code word is part of any other code word, correct? So, if you look from the root to the leaves, there is a unique path, so you can map it to a unique prefix-free code. And since no other code word is a prefix of any other code word, so you would not find any other code word in the path from root to the leaf. Okay. So, that is basically why I said a deary prefix-free code can be identified by a set of leaves in a deary tree, because from the root to the leaf there is a unique path, and since no other code word is part of any other code word, so no other code word will appear in that particular path from the root to the leaf. So, if you look at the way we would do this is, we would label these branches by this deary alphabet. Let us say I had d equal to 3, so I would say 0, 1, 2, 0, 1, 2, 0, 1, 2, and then from root to the leaf there is a unique path 0, 1, 1, 1, whatever it is, right. And with that you can identify each of these prefix-free codes. So, let us look at an example. So, I have these code words Z1, Z2, Z3, Z4. You can verify that this is a prefix-free code. So, 0, 1, 1 is not part of any other code word, 1, 0 is not part of any other prefix of any code word, 1, 1 is not prefix of any code word, and Z4, which is 0, 0 is not part of any code word. So, how do we map this to a prefix-free code? First thing we need to do is we need to identify what is d here. What is d here? D is 2, because we have 0 and 1, right. So, d is 2, and what is the maximum depth we have here in the code word? That is 3. So, let us draw a binary tree of depth up to 3. So, we start with a root here, we make 2 leaves, that is depth 1. We make 2 leaves here, makes 2 leaves here, that depth 2. We make 2 leaves here, 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 that is depth 3. Now, let us label the branches. Okay. So, let us call it 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Now, let us map the code word. The first one is 0, 1, 1. So, what is it? So, from the root 0, 1, 1. So, this is my Z1, fine. Z2 is 1, 0. So, 1 and 0. So, let us just delete this portion. Okay. So, this is 1 and 0, that is my Z2. Okay. What is Z3? 1, 1. So, that is 1, 1. So, that would be this. This is Z3. What is Z4? That is 0, 0. So, that would be 0, 0. So, I just remove this. Okay. So, I have mapped these code words to a deary prefix-free code, deary prefix-free tree, correct. So, the point I am trying to make is any prefix-free code can be correspondingly mapped to a deary tree, and we will use this tree to prove the properties of this prefix free code, like things like we want to find out what is the minimum number of bits required to encode this sequence, what is the minimum expected code word length. So those proofs we are going to make use of this DRE tree. Is this clear? What is a prefix free code and how we can map this prefix free code to a DRE tree? This I already had this. Okay. You can see here I have an unused node also here. There's no code word assigned to this, just noting it by this. Okay. Now I am going to tell you under what condition a prefix free code exists. So there exists a DRE prefix free code whose code word lengths are these positive number W1, W2, W3, Wk, if and only if this condition is satisfied. Now what does if and only if means? So we'll it works both directions. So we'll show that there exists a DRE prefix free code whose code word length is given by this if this condition is satisfied, and then we will show if this condition is satisfied and there exist positive numbers W1, W2, then corresponding code is prefix free. Okay. So let us first show that if there exists a DRE prefix free code whose code word length is given by this, then this condition should be satisfied. So let us prove this. In a full DRE tree of length n, dn minus w leaves stem from each node at depth w, where w is less than n. So what I am trying to say is, if you consider a full tree, let us just go back and draw a full tree. Let us just do it for n equal to 3. Okay. This is depth 1, this is depth 2, this is depth 3, right? And here n is, we have drawn full tree up to depth 3. So the point I am trying to make is, if you have a full tree of length n, d raised to power n minus w leaves stem from each node at depth w. Let us look at depth 2. How many leaves are going out from this depth w? 1, 2, and that is d in this case is 2, that is 2, 3 minus 2, d n minus 2, 2 leaves. Look here, there are 2 leaves which are going. So at depth 2 you can see there are 2 leaves. If you look at depth 1, how many leaves from, if you look at this node, 1, 2, 3, 4. If you look at this node, 1, 2, 3, 4, there are 4. So this is again 2 raised to power 3 minus 1. So is this clear that if you look at depth w, so many leaves are stemming out from that particular and from node at that particular depth, correct? So this is important because we are going to use this fact in our proof. So consider a full tree of length n, okay, and if you look at any depth which is less than n, then how many leaves are leaving nodes at that particular depth? This is the question I am asking. Okay. So I am saying the answer to that question is d raised to power n minus w, and I took an example to illustrate that. I drew a full tree of depth 3. So this will have total 8 leaves. Now I am looking at nodes at depth 2. So, this is this node, this node, this node, this node, and you can see at each of these nodes there are 2 leaves stemming out. From here there are this leaf, from this node, this leaf, this leaf. So, from each of these nodes 2 leaves are stemming out, which is nothing but d in our case is 2, n in our case is 3, and this is depth 2. So, this is this. So, this is precisely coming out to be 2. Now, if you look at depth 1, if you look at node at depth 1, this one, how many leaves are coming out from this node? So, this branch is going, this branch is going. So, this, 4 leaves are going. So, that 4 I am saying is 2 raised to power d is 2, n is 3, and w is 1. So, if similarly if you have a bigger tree like that, and if you look at any depth which is less than n, the number of leaves which are stemming from that node at that particular depth is given by d raised to power n minus w. Now, as I said, we are first going to prove that there exists a DRE prefix free code whose code word length is this, and we are going to show that if that is true, then this condition is satisfied. So, suppose there exists a DRE prefix free code. Now, let us construct a tree and map this DRE prefix free code to that particular DRE tree, the way we just mentioned. And how do we map them? We will construct a tree by pruning full DRE tree of length n, where n is the maximum of this wi, and we will prune this tree at all vertices corresponding to these code words, exactly the way we did in the previous case. We look at this code, we are given a code, prefix free code of length w1. So, what we will do? We will first draw a full DRE tree of length n, when n is the maximum of w1, w2, w3, wk, and then to map a prefix free code of length w1, what we will do is, we look at that code word, we go up to length w1, and then we will prune the tree after that, like we were doing. We remove the leaves which were beyond that and mark that as our code word corresponding to, prefix free code, correct. So, this is a procedure we are going to follow. Now, if you are going to follow this procedure, then remember at each, when you mark each of these prefix free code, you are actually pruning your tree. So, you are getting rid of some leaves. How many leaves are you getting rid of? Because you are going at depth wi, so you are getting rid of d raised to power n minus wi. So, we are going to use this fact now, and we are also going to use the fact that total number of leaves that we can remove is how much? D raised to power n, because that is the number of leaves. So, when we remove leaves at each step, total should add up to less than equal to d raised to power n. Okay. That is when we can map all these prefix free code to our tree, correct, and that is the condition. And if you simplify that, it will come to this condition, which is known as Crafts inequality. So, let us look at this. So, due to prefix free condition, if at depth wi we delete so many leaves, and none of these leaves would have been previously deleted. Why? Because it is a prefix free code. So, there is a unique path from the root to this leaf. There is no other code word in that particular path. Okay. So, these leaves that I am deleting now have not been deleted before. It is not happening that you deleted this earlier and then again you are deleting same set of leaves. Since total number of leaves are d raised to power n, so this many number of leaves I am deleting for the first prefix free code, for the second, third, for the kth I am doing this. The total leaves I can delete can at most be d raised to power n, right. So, do you agree that this condition needs to be satisfied? So, this condition needs to be satisfied if we want to map all these prefix free codes to our DRE tree, correct. So, if we simply divide both sides by d raised power n, we get this condition. Okay, we get this condition. Summation d raised power minus wi from I going from 1 to k, this should be less than equal to 1. Fine. Okay, any questions in the proof? Now we are going to show the converse of the proof, in the sense we are going to now show that if this condition is satisfied and if there exists a code of this length, then that code must be prefix free. Suppose W1, W2, W3, Wk are positive numbers such that Kraft inequality is satisfied. Now let us consider an ordered list of lengths. So we are reordering the these code words of length W1, W2, W3, Wk in the order, in the ascending order of their length, and by without any loss of generality, I am assuming W1 is the smallest length code word, then W2, W3, Wk, right. Now I am giving you an algorithm for mapping these code words. So how do I do this? Start with first code word of length W1, which is the smallest length code word. Remember, I have ordered them. Now these Wi's are ordered. So W1 is the smallest length code, W2 is the next smallest length, like that. Choose Zi as any surviving node or leaf at depth Wi and prune the tree. So what I am going to do is, I am going to go up to depth W1 in that tree. Okay, so I have a full DRE tree. I am going up to depth W1 and then prune that leaf. And I repeat this for all W2, W3, Wk. If I am able to prune my tree every time, that means I am able to map all of them, this thing, into this, right. So is the algorithm clear? I am first arranging them in the ascending order. I will tell you why I am arranging them in the ascending order is important here, because I do not want to delete same set of leaves twice. What would have happened if I would not have started with the smallest length? Let us say I would not have started with the smallest length. Let us say I started with some length which mapped my thing to here. So I would have deleted these, and if a smaller length would have come, let us say at depth 1, then I again would have been deleting the same set of leaves, which I want to avoid, because I do not want to so what I am doing is, I am starting with the smallest depth. So I am deleting maximum number of leaves there. So if I start here, these leaves are all deleted. Okay. So when a larger length code word come, I am not going to touch, I am going to go to a different part of the tree. So that is why this ordering is important here. Ordering is the way I map them, this ordering is important here, because I do not want to delete the same set of leaves twice, and that is why I am doing this. So I am arranging them in the ascending order. Now what I do is, I choose that as any surviving node or leaf at depth Wi and then prune the tree. I stop if there is no surviving node or leaf, otherwise I continue, and I do it for all k. Now, so let us say we are able to choose Zk in step 2, we are able to construct a prefix free code. So suppose, so we want to show that the way we are mapping these code words into a DRE tree, we are going to show you that if Kraft inequality is satisfied, then we should be able to complete this step, meaning for all W1, W2, W3, Wk, we should be able to map them to a DRE tree. And if we are able to map them to a DRE tree, we know there is a one-to-one correspondence between a DRE tree and a prefix-free code. So we know that these are all prefix-free code, right? So now I am going to show you is that this algorithm will be successful provided Kraft inequality is satisfied. So I am saying, let us say, suppose Z1, Z2, Z3, Zi minus 1 has been chosen. I have already mapped Z1, Z2, Zi minus 1. Now I want to see whether I can map Zi. Okay. How many surviving leaves are remaining? My total leaves were d to power n. In first step I deleted this, second step I deleted it, at I minus 1 step I am deleted this many leaves. So how many surviving leaves are there? That is this. Is this number non-zero for I less than equal to k? Is this number non-zero? When Kraft inequality is satisfied from 1 to k, this is less than equal to 1. So that means for any I less than equal to k, this number is non-zero. So if this number is non-zero, that means there exists a node or a leaf where I can put this code word. You understand what I am saying? What I did was up at step 1, step 2, step 3, step I minus 1, I deleted so many leaves. Now I am left with this many leaves. Now this leaf, because Kraft inequality is satisfied, so from j1 to k, summation of this is less than equal to 1. Now in this case my I is less than equal to k, so when I go up to k, this number is still less than basically 1. So this number is then non-zero. I have a non-zero number of leaves still remaining. That means I still have some leaves or tree, some leaves and nodes in my tree which have not been pruned or which have not been mapped to any code word. So I can put my Zi there, and this I can do as long as my I is up to k. Why? Because from j1 to k minus 1 summation is still less than 1, because Kraft inequality says that this summation from 1 to k is less than equal to 1. So what I have shown you is this algorithm which I proposed for mapping these code words of length W1, W2, Wk to a DRE tree, that algorithm will be successful as long up to I equal to k, correct. So if I am successful, that means I have already mapped my code word. If I am able to map all these code words into a DRE tree, that means these are all prefix free code, because it is a unique map from the root to the leaf of this tree. So because Kraft inequality is satisfied, this number is positive. So I still have some leaves and nodes available. Therefore the number of surviving nodes is greater than 0. So if there is surviving leaf at depth n, then there must be some unused node also at depth less than. If I see this node is unused, right, that means in this whole path these nodes are not been used, correct. So what I am saying is, if there is a surviving leaf at depth n, then there must be some unknown unused nodes at depth wi less than n, and I can always map my Zi, which is length wi, could be n, could be less than n, I could map it as Zi. Is this clear? So If there is unused leaves here, there is an unused leaf here, there will be unused node here, unused node here. So, no matter what my Wi is, I can map it there, and this process will be successful for I up to k. Hence, I have mapped all these. So, what I have shown you is, provided Craft inequality is satisfied, I have mapped all these code words of length W1, W2, W3, Wk to my DRE tree, and hence I proved that these are all prefix free code, because I can map all my prefix free code to a DRE tree. Fine. So, I have proved both sides. I have basically shown that if prefix free code exists, then Craft inequality has to be satisfied, and I have shown if Craft inequality is satisfied and you have code words of length W1, W3, Wk, then this code must be a prefix free code. Okay. So, this shows, so whether a prefix free code exists or not, we have to first check whether the Craft inequality is satisfied or not. So, let us consider a ternary prefix free code, where code word length is given by, so ternary means D is 3, quaternary will be 4, and W1 is 1, W2 is 2, W3 is 2, W4 is 3, W5 is 4. So, first thing that we need to check is whether a prefix free code exists or not. So, we are going to apply Craft inequality, and we found out that this is less than 1. So, prefix free code exists, and then how do we go about it? You look at what is n, that is the maximum of Wi. So, this is in this case is 4. So, you construct a full ternary tree of depth up to 4, and then you arrange this Wi in the ascending order, they are already arranged. Okay. So, you start with this one. So, you go here and then you prune all the tree which was beyond this, you go for 2, prune it. So, you do this process. Because Craft inequality is satisfied, you would be able to map these code words into this DRE tree, and then you label these branches by the alphabet. So, you know that, okay, so this one is 0, this is 1 0, this is 1 1, this is 1 2 0. So, you can find out the code word corresponding to each of these code words of length Wi. Okay. So, that is how you basically map them to a prefix free code. Is the procedure clear? Okay. Now, I am going to prove, I am going to define few things, and I am going to use them to prove what I said was I want to compute a lower bound on what is the expected code word length required, and I am going to show that that lower bound is related to the entropy. So, by rooted tree with probability, we mean a finite rooted tree with probability assigned to each vertices. And how are we assigning probability? The root is assigned probability 1, and probability of every node is sum of probabilities of the nodes and leaves at depth 1 in the subtree stemming from the immediate node. Root will have probability 1. So, this has probability 1. Now, what is the probability of this? I am saying it is the sum of probabilities of the nodes and leaves at depth 1 in the subtree stemming from this intermediate node. So, I am looking at this. Now, what are the nodes and leaves at depth 1 from this? This one and this one. So, the probability of this node would be probability of this node and this node. Now let us look at, let us say, this node. What will be the probability of this node? This will be this node and this node. Now let us change this tree little bit. Let us say if I have a tree of this form, again a binary tree. Okay. Let us say looking at this, what will be the probability of this node? This will be this node and this leaf. So you have to look at depth 1 from that particular node, and if when you look at depth 1 from that particular node, it could be either a node or it could be a leaf. That is why I wrote here it's sum of probabilities of nodes and leaves at depth 1. We could have all the nodes, or we could have all the leaves, or we could have node and leaves, but you have to look at depth 1 from that particular node and you sum of their probabilities, that is the probability of the node. Okay. So this is how we are defining a rooted tree with probabilities. Now I am going to give a result which is known as path length lemma. So what does this result says? In a rooted tree with probability, the average depth of the leaves is equal to sum of probabilities of all nodes including root node. So what I am saying is I have a rooted tree with probability and I am interested in finding what is the average depth of the leaves. How do you find the average depth of the leaf? Length of the, basically, so where the leaf is from the root multiplied by the probability of occurrence of that particular leaf, you sum it over all the leaves, that would give you average depth. Now what I am saying is that average depth is nothing but sum of probabilities of all nodes. Remember, I am using the word nodes, not leaves. Sum of probabilities of all nodes including the root node. Okay. How do I prove it? So probability of each node is sum of probabilities of the leaves in the subtree stemming from that particular node. Okay. A leaf at depth d appears in d nodes on the path from root to the leaf. If I have a leaf here, okay, what is its depth? 1, 2, 3, 4. It has some probability, let us call it pi. Now this probability is appearing where? In this node, because this node probability will be this plus this. This is appearing, it's appearing here because this pi is appearing, so it will appear in 2, 3, 4. So the point I am making is a leaf at depth d will appear in exactly d nodes on path from root to the leaf. So in the rooted tree with probability, the contribution of this probability will appear here, will appear here, will appear here, will appear here. It will appear 4 times, and that is precisely what its length is. You take any other leaf, take this leaf. What is its length? W is 1, 2. Its probability, let us call it Pj, it will appear here, it will appear here. So every leaf at depth d is going to appear d times in the probabilities for the nodes from root to the leaf, correct? Now if I add up then all the probabilities of the nodes, what am I doing? I am actually, if so, sum of the probabilities of node is equal to sum of product of each leaf probability multiplied by its basically depth. Why? Because look at, so this contribution of this is appearing here, 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 contribution of this is appearing here, 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 here. If I just add up, contribution of this is appearing here, here, here. So if I just add up all the nodes probability including the root node, what will I get? I will get this probability multiplied by the depth, 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 correct? So this is precisely what the proof is. So if I sum up all the nodes including the root node, what I am going to get is sum of product of each leaf's probability multiplied by its depth basically, and that is nothing but average length of the average depth of the leaf. Fine. So path length lemma says if I want to find the average depth of the leaves, what I need to do is I just need to add up all the nodes probability including the root node, and remember I am adding the probabilities of the nodes, not leaves. Is this clear? Okay. Just take an example. We will do it both ways. We will first by brute force compute the average depth of the leaf. So that is 0.1 into 1 plus 0.2 into 1 plus 0.3 into 2 plus 0.4 into 2. That would be how much? 0.1 plus 0.2 will be 0.3 plus 0.6 and plus 0.8. So that would be 1.7. Now let us use path length lemma. So this is a rooted tree with probability. What is the probability of this root, this node? 0.7. This is the probability of this plus this. So this is 0.7. What is the probability of this root node? 0.1 plus 0.2 plus 0.7, that is 1. Okay. Now apply path length lemma. It says add up the probability of all nodes including the root node. So what are the nodes which are there? This is a root node and this is a non-root node. This, it has probability 1, this probability 0.7. We get 1.7, which is what we got by brute force, correct? So if you want to find the average depth of the leaves, what you need to do is you can just add up the probabilities of the nodes. Is this clear? Okay. Now I am going to define few things. What is a leaf entropy and what is a branching entropy. So what is a leaf entropy? So a rooted tree with t leaves whose probabilities are given by p1, p2, p3, pt, the leaf entropy is given by this. Now in a dairy tree, what are the leaves? These are nothing but my code words, these are UIs. So leaf entropy is nothing but h of u. U takes k possible values, they are essentially mapped as leaves in my tree, right. So this leaf entropy which I am defining is nothing but this is h of u. Okay, now let us look at this definition of branching entropy. Suppose qi1, qi2, qi3, qil are the probabilities of the nodes and leaves at the end of li branches stemming outward from a node whose probability is pi, then branching entropy of this node is given by qij by pi log qij pi minus of that and sum over all the branches. So what I am saying here is I have a node, let us say I have a node here and this node probability is capital Pi, okay, and Qi1, Qi2, Qi are the probabilities of the nodes and leaves at the end of L branches stemming outward from this node. So, what are the branches stemming out from this? This one and this one. So, I am saying this is, let us say, Qi1 and this is, let us say, Qi2. Okay. Then how am I defining branching probability? Given that probability of this is Pi and this probability is Qi1 and Qi2. So, this is the probability of selecting Qi1 by Pi is the probability of selecting the upper branch, Qi1 by Pi is the probability of selecting the lower branch, given that I am at this particular node. Okay. So, this is how you define branching entropy. Okay. Now, I am going to show you a result which links branching entropy with this leaf entropy. Okay. So, again, these are this Pi is the probability of the node from which nodes and leaves are stemming out, and the probabilities of those nodes and leaves are Qij's. So, if you look here, leaf entropy, these are the probabilities of the leaves. So, leaf entropy is given by that minus 0.1 log 0.1 minus 0.2 log 0.2 minus 0.3 log 0.3 minus 0.4 log 0.4, and log to the base 2, that comes out at this much. And if you are interested in branching entropy, let us say I want to find the branching entropy here. So, this node probability is 1, and what is the probability of this? 0.1, 0.2, and this is 0.7. So, this will be 0.1 by 1, 0.2 by 1, 0.7 by 1. So, that is this. And if I want to find branching entropy here, so this will be 0.3 by 0.7, 0.4 by 0.7. So, that will be 3 by 7 and 4 by 7. So, this is my branching entropy. Now, we are going to show an interesting result which links these two, and we will use that result to prove a bound on our expected code word length. So, this leaf entropy theorem says the leaf entropy of a rooted tree with probability is equal to sum over all nodes, including the root node, of the branching entropy of that node weighted by the node probability. So, what I am saying is the leaf entropy is given by branching entropy multiplied by the probability of that particular node, and when you sum this over all the nodes including the root node. Okay. Now, let us look at this proof. Now, by definition of this rooted tree with probability, what is the probability of the node? It is nothing but probability of the nodes or leaves stemming from that particular node. So, that is this, correct? Okay. Now, just a second, in the branching probability expression, I have this log Qij by Pij. Okay. And I am doing Pi Hi. So, this will cancel out. What I have is Qij log Qij Pij minus of that, right. Now, what I am saying is, so log Qij Pij I can write it this way. Okay. Now, so Pi Hi can be written in this particular way, because the Pi denominator gets cancelled when I multiply it by this. So, what I get is this. Now, the point I am making is, if I sum this over all the nodes, I get leaf entropy, right. So, what I need to show is, when I sum it over all the nodes, everything else cancels out, only thing that remains is this leaves. Okay. Now, let us look at this term little closely. This is a minus term here and there is a plus term here. This is probability at the node, this is probabilities at nodes and leaves stemming from that particular node. So, this is adding minus, this is adding plus. Okay. Now, let us look at three categories of node. First is root node, second is leaf node, well not leaf node, meaning we will look at root node and we will look at all other nodes. We will look at nodes from where leaves are stemming out. So, let us so the claim I am making is as follows: a non-root kth node will contribute plus pk log pk to the sum corresponding to that I equal to k, and it will contribute minus pk log pk sum to the term for I such that the node k is at the branch leaving node I. So, the net contribution is 0. Now, what am I saying? If you have any node other than the root node, its net contribution is 0. Why? I had two terms there, remember? I had pi log. So, let us look at this particular node. There were two terms there, pi log pi and then minus summation qij log, right. Now, this pi, this is pi for this node, but this is qi for this node. You understand what I am saying? You look at any non-root node, it is pi for that particular node, but for node before that, it is going to be qi. So, the net contribution of that particular node will be 0, because when I add this node probability, it is adding plus pi log pi, but when I will add this, this will give me minus, because my qij is this. So, the claim I am making is, you consider all non-root node, their net contribution will be 0, except, we will come to that. Let us look at except one case. So, basically root, let us look at root also. So, root is not qi of any other node, because root is the end, right. So, root will contribute only pi, it would not give any qi. So, and what is the probability of the root? 1. So, log of 1, that is also 0. So, what is remaining? Look at the leaves, look at the leaves, leaves are only qi's, leaves are never node in themselves, right. So, if you look at any node which has a leaf, not any other node which has a leaf, this leaf is only contributing in that qi term, it will never contribute in pi. So, when you add up our nodes which have a leaf ending, that contribution is never going to get cancelled out, because that leaf is always going to contribute minus qij term, it would never be a node. So, when you add over all the nodes, any non-root node which does not have a leaf, they will all cancel out, and any non-root node which has a leaf, only the leaf probability will remain, others will all get cancelled out, and the contribution of the root node is also 0. So, then when you sum over all the nodes including root node, what is left? The leaf probability, right, and that is what this theorem says, that summation pi hi over all the nodes including the root node is equal to the leaf entropy. And what is our leaf entropy? Our leaf entropy is nothing but h of u, because our code words are basically at the leaf. correct. So, this is a very interesting result, because we are going to use this result to compute, we are going to use this result and the path length lemma to prove a lower bound on the expected code word length. Okay. So, now we have all the tools available to compute a lower bound on expected code. What is the minimum number of bits required to represent your source? Given you have been given a random variable u, which takes k possible values with probabilities given to you. So, what is the minimum number of bits required to represent that source when you are doing this block to variable length coding? So, h of leaf is this, you know this, and branching probability is upper bounded by log of d. If you look at, basically this is branching probability, like how many our code word we are output code word is basically we are considering as a DRE code word, right. So, how many branches are leaving from the each node? D. And what did we say about discrete entropy of a discrete random variable? It is lower bounded by 0, upper bounded by log of number of possibilities. Here the number of possibilities is d, because it is a d, our output code word is a DRE code word. So, it is upper bounded by log of d. So, these two things are clear. Now, we are going to make use of path length lemma. What does path length lemma and path length lemma as well as this leaf entropy theorem? Leaf entropy theorem says h leaf is equal to summation over all nodes pi hi. Now, what I did was I replace h leaf by this. This is equal to summation pi hi. Now, hi is upper bounded by log of d. So, I have this, and this is summation pi. So, I am essentially using this result h leaf is summation pi hi, and I use the result that hi is upper bound by log d. So, that does not depend on I. Okay. So, this h leaf can be written as log d summation pi. This is what I am doing. Now, tell me what is this? I am summing over all nodes including root node. Average depth of the code word leaves from path length lemma. This is nothing but average depth of the leaves, and what are there in the leaves? Those are my code words. So, this is my expected code word length. You understand what I am saying? So, this from path length lemma, this is expected value of w. Okay, that's what I. So, now I have a bound on. So, I can write expected code word length is basically lower bounded by hu log of d. So, I know if I want to do block to variable length coding, what is the minimum number of bits required to represent the source? That is basically given by this. This is an important result, because this gives a lower bound on okay, what is the minimum number of bits required to represent your source. And the reason I was mapping this prefix free code to a DRE tree was because I am going to use those properties to prove this result. Okay. Right. Prefix free code I have proven that this is the condition, this is the minimum number of bits required. Okay. Now, let us go over a very simple example of prefix free code. if I choose my code word length as ceil function of minus log of the probability of occurrence of ui, then basically first thing I can show is, if I choose my code word length to be this, craft inequality will be satisfied. If craft inequality is satisfied, that means prefix free code exists. So let us look at whether craft inequality is satisfied or not. So this is minus of ceil function of this. If I remove this ceil, I am raising it by a smaller number, but minus of that. So this will be less than equal to this, and this can be written as this, which is 1. So I have shown that if I choose my wi in this particular fashion, then craft inequality is satisfied. So in Shannon-Fano's code, code word lengths are chosen in this particular way. Okay. So you are given a random variable u, carry random variable, which basically, and you know the probabilities of occurrence of u1, u2, u3, uk. What you need to do is, using this, find out wi. Once you find out wi, you know how to map it to a prefix free code. Same procedure, you draw a full DRE tree of length n, where n is the max of wi, and then you arrange them in the ascending order and start pruning the tree, and you basically assign your code words. So this is how, and then you label the branches of your tree. So that is how you can get the prefix free code. So that is basically your Shannon-Fano prefix free code. I will just take an example to illustrate that. We can also get an upper bound for this Shannon-Fano code. I am just skipping it. Let us take an example. So I have a binary Shannon-Fano code. Consider a binary Shannon-Fano code for a Fourier random variable, so which takes 4 different values with these probability, and I am interested in constructing a binary this thing Shannon-Fano code. So I have been given these probabilities. So I need to first compute these wi's, that comes out as 2, 2, 3 and 4. So maximum wi is 4. So I will construct a full DRE tree of depth up to 4, and then I start pruning them at depth 2, 2, 3 and 4. So what you will get is something like this, and then you label the branches. So your code words are 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0. So these are your code words. Okay. Now you can see this is not an optimal code. In fact, I skipped this result. What we can show is the expected code word length lies between entropy plus 1. So if entropy is very large, this code is fairly good, but if entropy is small, this code is not very good. If you look here, the entropy here is 1.846. So what it says is Shannon-Fano code will be between 1.846 and 2.846, which indeed it is 2.4, the average code word length. But if each of you would have been, let us say 1000, then that is pretty good, if I am getting a code which is between 1000 and 1001. Okay. Now in the next class, next lecture, I am going to talk about how to design an optimal prefix free code. And when I say optimal prefix free code, that will give the best possible expected value of w. Okay.